show too many slides. Um, Hi, how are you guys doing? So I'm TA, aka Fake Dev. I'm a ZK engineer from Chroma. So today I would like to share our experience of advancing OP stack into ZK Rollup. So we're trying to enhance efficiency and security with zero knowledge proofs. So for those of you who don't know about Chroma, I want to first celebrate our successes from last year, our mainnet launch. So we were one of the projects built on OP Stack. So we were one of the first. I mean, we were the very first optimistic rollup with an active fault-proof system. So we utilized ZK proofs for it. And so ZK enables to solve some problems in traditional fault-proof systems. And first, we approach with a circuit-based implementation of ZK provers, but it has a very, very big issue. So we're trying to transit from circuit-based approach to zkVM-based approach. And lastly, we're also building a ZK backend library to push the boundaries of proof generation speed. So why ZK fault proofs? So in traditional fault-proof systems, it requires a lot of interactions, which leads to high bond amounts, which decreases the level of decentralization. So with ZK fault proofs, we can just narrow it down to a block level instead of instruction level, which requires much less interactions. So it not only reduces the operational cost itself, since there's less interaction, so we need less computation, but also it can significantly reduce the bond requirement. So it naturally leads to better decentralization and security of the network. So moreover, for like Arbitrum's bold, if we apply ZK technology into it, we would be able to reduce the bond requirement significantly. That is usually used for blocking Sybil attacks. Also, Optimism is putting a lot of resources into exploring ZK fault proofs. So we have an announcement that we have received Retro PGF Round 5 from Optimism to explore more on the ZK fault proof side. And this recognition, I think, shows how much important and possibilities are there into building a permissionless fault-proof system with ZK. So we've looked at like our achievements since last mainnet launch, and now I would like to share some our lessons learned and challenges that we've experienced for building ZK fault-proof systems in our mainnet. So the very important fact that we learned is that the circuit-based approach is just not sustainable. So we currently have about like 100K lines of code, which are for custom circuits. So we have to write it in a circuit language like Plonkish. And it's very, very hard to write and debug and verify. So what we're trying to do is check the integrity of EVM state transition function. But we need like several specific custom circuits written in circuit languages to verify that the state transition function, given the input, is done correctly. And back in 2022, Vitalik even mentioned at the time there was no like production-ready zkEVM circuit codes, but they had a POC version of it in Ethereum's PSC. And back in the days, it was like 35K lines of code, but even Vitalik mentioned that it's never going to bug-free for a long, long time. So it's very prone to errors, very prone to human errors. So to sum up, there are two challenges. Writing the circuit itself is tough because it's hard to audit and debug. And also, since Optimism and Ethereum brings upgrades to their mainnet, to support like full compatibility, we have to keep up with the protocol upgrades they're making, which means that we have to modify circuits again and again every time the upgrades come up. And this could lead to, like, possibly if we make more modifications, then there will be possibility of more errors, which would like harm our security of our mainnet. So we need a better approach. So now we're trying to take a zkVM-based approach because zkVMs can give us generality and auditability. What it means is, as I mentioned, in a circuit-based approach, we need to write circuits in a circuit language like Plonkish, which is very unfamiliar. And because of that, the auditors will also have a hard time auditing, and even us can't really verify well that our code is written well. But zkVMs allow us like flexibility. We can write any program that we want to verify the computation in Rust, and since it's written in Rust, it's very, very better to audit and debug. So now I would like to dive in more to zkVM area, so how we're trying to move on from circuits to zkVMs. So as I mentioned, zkVMs can provide a general purpose environment for verifiable computation. So what it means is that we don't need to implement circuits anymore. We can just write Rust program, and zkVMs can basically execute the program and give a proof which proves that the computation was done correctly. So how it works is, first, each zkVM vendor would have a compiler toolchain that can compile a Rust program into, let's say, if it's based on RISC-V, it would turn into a machine code based on RISC-V. And then inside of zkVM, there's an executor which executes the program and generates what's called an execution trace. Execution trace is basically polynomials bound by some constraints. So back then, we would have to write like circuits to represent some input data into a polynomial and then have constraints for it. But now zkVM circuits could handle that. So now we can just write Rust code. There's more flexibility. And then in the proving stage, where the zkVM gives a proof based on the execution trace, it would commit to the trace and then generate a proof. So I have a summary kind of picture that we can compare, like how it's different. So the colored green parts are the code that we used to maintain and we have to maintain. So back then, we would have to maintain like zkEVM circuits written in Plonkish. So there would be like EVM circuit, RLP circuit, MPT circuit, and transaction circuit, which kind of replicates the behavior of EVM. So it will verify the logic if let's say the transaction body and like the block header and block body comparing with like hash it and then like compare with the block hash. That's what we used to do, but it's very, very tricky. But now, since on the right side, there are zkVM circuits, so zkVM circuits would handle that, and instead, we would just write a block execution program, which for us, as an Ethereum layer 2, we would derive the batch from L1 and then execute it on L2. So that would be the program we were trying to write. And some of you might ask, like Vitalik mentioned in 2022, we launched our mainnet in 2023, and then like, why didn't you guys first approach with zkVMs at first, right? Like, why did you guys write circuits and do all that hard work? That's because back then, zkVMs were not like performant. So since the proving time is long, within the challenge period we have, there can be possible vulnerabilities, possible attack vector for delay attacks. So that's one of the reasons why we chose a circuit-based approach. But now, RISC-0 calls it continuation, and like SP1 calls it sharding. Like there was a breakthrough called sharding, which with the full execution trace, you can now divide it into a unit called shards. So it's usually represented in the number of cycles of RISC-V. So SP1, they kind of have an optimal number of like 2 to the power of 22 cycles for each shard. And since we can divide it into shards, now we can parallelly generate a proof for each shard and then compress it later into a single shard. So now there's more and more upside in terms of throughput, since we can parallelize proofs. So that's what we're trying to do, and we're almost there shipping it to the mainnet. And now I want to share more of my thought that what we can explore more in the future to overcome barriers to become from an optimistic rollup to a zk rollup. So my concerns about zkVM-based approach is, since zkVM vendors' business model is usually running a prover network. So they get a delegated proof, and then they generate a proof for it, and then return the proof to the client. But there might be a situation where zkVM prover network might fail. So usually zkVM vendors, since they've built their zkVM, they're very, very good at giving a good performance. So usually they would have a cluster of machines, and then they would split the workloads to each machine, and then orchestrate it, and then create a proof and return. But since most of the such prover network related codes are closed sourced, maybe to handle this kind of network reliability issue, us Chroma might have to implement a code to orchestrate multiple machines so that every validators could I'm not sure if this is correct, but they might have to run a cluster to generate a proof for the network. So another concern might be, so now there's going to be more stage 1 rollups, but for stage 2, we only want the security council to come in and resolve the problem if the failure is only on-chain provable. But currently, in my perspective, for the zkVMs, currently there's no way to make the network failure to be on-chain provable. So that's another concern. And also, since we cannot overlook the fact that zkVMs itself might have a bug. So what I think is we need a multi-prover system so that we can compensate the bugs for that. So then in that case, the goal would be to enhance the security of the network, but not much with the overhead. So we don't want periods to be longer. So there might be 3 types of multi-prover schemes instead of having a single prover. So one, I think most of the networks like Scroll and Tyco is trying to use T's. But in my opinion, there's a trust issue that we have to trust the T implementation itself. So, and there's also Hydra centralization problems. So we might have to come up with a clever idea to maybe use 3 vendors of T's and then have a multi-sig kind of thing. And another one would be kind of very, very labor intensive, but come up with another circuit-based zkEVM. So instead of Plonkish and Halo 2, you might have to write another zkEVM code, circuit code, with another language. I don't think no one will try that. And I think the best would be our approach to have another zkVM-based zkEVM. I'll tell you why we think this is the best. And if we have a multi-prover system and if we have zkVMs now, we could really, really easily ship zk rollups than past 1 or 2 years. But I've did some benchmarks with several zkVMs, but there's still a feasibility issue. So first, there's a cost barrier, which is very, very important. And in my opinion, it would be really, really hard to charge the users to use it, since most of the layer 2s and most of the optimistic rollups now have very, very cheap fees. So there are 3 types of costs that we need to pay to run a zk rollup. First, it's the biggest bottleneck, which is the proving cost. So I've tested with a network with about 3 TPS, and you need about $1 million for proving the blocks for a year. So I think it's not that feasible now. And also, we would have to commit to the batches we've settled into layer 1. So there will be settlement fees also. And to finalize the blocks, we would have to send the proof to the contract and verify on-chain. So there's also going to be verification piece. But that's going to be really, really small because we will be able to aggregate proofs inside a zkVM, which will be way cheaper. But there's going to be trade-off between finality. And also, we could explore more on future directions where I introduce the multi-prover system. And also, the zkVM vendors would have to consider more about prover decentralization, where they don't keep the clusters running on only their network and getting proof requests, but instead of like have an incentive mechanism so that prover network can be decentralized a bit more. And like we're also at the same time pushing the boundaries of proof generation. So we have our own very unique open source library called tachyon, which is a particle that's known to be faster than light. And it's basically a modular zkVM, zk backend library. And we also have a feature of GPU acceleration. So since we've built our zkVM based on Halo 2, we first optimized Halo 2 a lot. And we have about like 1.5x, 6x faster benchmark. And we also are trying to utilize SP1 zkVM at the moment. So we also optimize Plonky 3 as well, which is used by SP1. And last, since Circum is very, very widely used in the community, we also optimize a lot in terms of rapid snark. So it's also faster. And we could wrap up into this one figure where if Chroma has a multi-zkVM prover backing the network, we would also have Tachyon, which is a modular zk backend library, which could support all kinds of zkVMs. So we would only have to maintain the very front like zkVM main, which is written in Rust, and which mainly uses the library Kona, which is maintained from Optimism, which has block derivation logic and execution logic. So we could easily write a program for our mainnet within like 200 lines of code. And we would have an input which would be the block we were trying to prove. And we would have a multi-prover like one of the frontiers, RISC-0, SP1, O1VM, Valida maybe. And then we have a tachyon, which is backing with powerful GPU optimizations, which will accelerate the proof generation speed. Yep, that's it for today. And you can contact me with fakedev9999 on Twitter, Telegram. Please contact. We could share more about fault-proof systems. I would like to hear your ideas. And that's it. Thank you.
Yeah, you can just stay over here. All right, great talk, TA. So thank you to the crowd for submitting all these amazing questions. We do have less than 5 minutes to go through some of them. Let's go through the most upvoted one. How is it different than OP succinct?
Yeah, some of you guys might know and not know, but OP succinct and us, we have a very, very similar logic. Actually, we were working underwater like for about like 2 months, and then like we shared it to the SP1 team about, oh, we have a Chroma SP1 prover repository. You could take a look if the logic would be correct for zkVM based prover, and they were also working underwater with the same thing, and like it comes out that like we have almost similar logic, and they have an additional feature of what I mentioned of aggregating the proofs. So the logic is very similar, but basically we built the same thing.
So I'm going to mark this as answered. Any stats on prover cost, specs, and time?
So the prover cost for our fault-proof system, for about a block with a TPS of 3 to prove a faulty block of TPS 3, I think it costs about like currently, so it depends on the pricing of the prover network you're trying to use. But if you're just using an on-demand plan, which would be the most expensive per cycles, if I remember correctly, it was about like 20 bucks for a block with like about like TPS3. And the stats and like the machine specs, it's not revealed at the moment for SPO1 prover network, so I'm not sure about that.
All right. Do you know if the ARB ecosystem have similar plans?
Yes, I definitely know, and I also know the fact that they have a fast withdrawal feature now with zk proofs. I didn't have much time to like deep dive into it, but I definitely think like Arbitrum also is going through the right path, so maybe we could collab more and talk more about it.
All right, great. So we can go through, I guess, 2 more questions real quick. In your prior implementation by Plonkish Circuit, you mean Plonky 2 or 3 or something custom?
Oh, it's actually Halo 2's Plonkish arithmetization. It might have like confused you a little bit, but we're using a backend currently, Halo 2.
All right. So one last question: what happens if the guest program panics? Can you still produce a proof?
So if a guest program panics, then you can't produce a proof. So I'm not sure the person who's asking the question like is intentionally panicking the program or not, but like yeah, if it's a bug that's causing panic, then proof is not produced. So this is another thing I mentioned in the slides before is we need a way to like overcome like if the program panics, like, but if it's a bug inside a zkVM or if it's a bug in a program, then like we would need to way to verify it on chain or like have a way to prove it on chain so that security council could like intervene or what.
All right, great. So our time is up. Thank you so much, TA.